Yeah. I try to answer them as I can because I spoke to Merson last week about this, and then he said, "Oh, don't talk about some things. Talk about some things. It's fine."
And he
So
was a PhD student in his first year of doing his PhD, but he did his undergrad here at UNSW as well. So
yeah,
he's been through it with you guys.
okay. All right. So I'll just go through this course. So CVEN2101. The main thing about this course now, it's just it's very easy to be honest. Once you know what you need to know, essentially you don't have to learn much from week 1 till week 4 anymore because it's already tested it during the midterms. In terms of this finals exam, it'll be from week 5 to week 10. So the main thing you should know it's about the permanent structures, the construction sustainability, and then the 3 weeks of the economics. So I'll just go through those topics really quickly over here so that I'll leave some time if you have to ask any questions. Yeah. Okay, so week 5, we talk about permanent structures. So in week 5, as I recall, I didn't do this tutorial because it was the midterms and Emerson decided to do it during the lecture hours. Essentially, I'll just go through the calculation question. So if you are not aware, the final exam will be, I think, multiple choice questions and the calculation question. It'll be probably the same format as the midterm. So in a way, your workings don't really count. It's just the final answers that count. So try to get that right. So just want to go through week 5 again, permanent structures. So you have not heard it from me, you've heard it from Wilson. So essentially, I'll just go through the questions. This is the workshop questions. So essentially now we have a client and this client wants to construct a storage room with this particular dimension, so 4 meters by 6 meters by 2.8 meters. So it has a door, it's 90 centimeters wide and 1.8 meters tall, and also 2 windows with the size of 1.8 meters by 1.2 meters. Please bear in mind the wording over here. Pay attention to the number of windows and the number of doors. Sometimes he puts the numbers in it. He puts like 1 or 2, 3, or sometimes he just spells it out like that. Just take a pointer. Okay, so then the floor it's gonna be 100 mils concrete slab, 2 layers of steel mesh of SL82. So what this SL82 is, it's just a type of reinforcement. So there's SL80, SL82, so on and so forth. So that will determine the number of the amount of steel required. The roof will also be a concrete slab. I don't think there's any houses built like this. It's like a prison of sort. So it has a concrete slab on the bottom and concrete slab on top. 200 mil thickness with N16 steel bars. At the bottom, at 100 mils in both directions, and 1 layer of SL81 on the top. So if you can imagine, it's bars and then you have this mesh on top of it. So this is sort of what it kind of looks like. So you have the 2 windows over here, and then you have the door over here. So I don't know if he's gonna put in like a schematic drawing like this, but for those of you who might not have taken architectural courses before, something that looks like this is a window. So if you have a wall and then it has this line through the middle of it, it's a window. And then if you have this thing with a quarter circle on it, it's a door. So question part A asks how much steel and concrete are required for the on-ground slab. So now the question just asks for the slab we have as the floor, how much concrete and steel do we need? And considering that it's $600 per cubic meters and $3,800 per ton for respectively. So if he puts it like this, then your concrete would be $600 per cubic meter and your steel would be $3,800 per ton. Another clue that you can look for, concrete is being sold usually in the market in terms of cubic meters, and then steel is sold per ton. Okay, so then you don't get those things mixed up. The fixed price of the steel fixings, formwork, and concreting is $1,000, and so the question asks how much will the cost of that on-ground slab be? Allow 5% extra concrete and 20% extra steel for waste and overlapping. So this bit over here, it's, well, in an exam, it's just something additional you put in, but in real life, this is one of the most important bit because you don't want to order too little. It's okay to order a bit too much, it's because if you order too little, then you might have like a wonky shaped slab, and once it hardens, you might have to break it again. So moving on, so this is what an SL82 mesh look like, essentially. So it has all this spacing over here. You have all these criterias. So moving on. So the required, I'll just do it over here because it's for recording. Usually in my class, I write it on the board. So the required concrete for the ground slab. So we know the dimension of the house of the shed is 4 meters by 6 meters. We know that the thickness is it's 150 mils, so it's 0.15 meters, right? And then this 1.05 just is the waste, right? That 5% extra waste. So you need to take that into account. The size of the SL82 mesh, so it will be 6 meters times 2.4 meters, so it's 14.4 square meters. So if you're wondering where this 2.4 meters come from, it came from over here. So the mesh, it looks like this if you look at the dimensions at the bottom. So what this is saying is if you read it, 29 spaces at 200 mils, 6,000 millimeters. So what that is you have 29 spaces, so 29 holes in it, at 200 millimeters apart, and the length of that thing is 6,000 millimeters, sorry. So, and it applies the same as the vertical region over here, right? So it's just 6 meters times 2.4 meters, so it's 14.4 square meters, and your weight is 52 kilograms. So, the total mesh weight would be equal to your floor area divided by the mesh area. So what that means is you will get the number of mesh needed for one layer, right? So if it's 4 meters by 6 meters, how many of those sheets, if you can imagine, you need? Multiplied by the number of layers, right? So if it's 2 layers, 3 layers, could be whatever. Multiplied by 1 plus the waste percentage. So with steel, it was 20%, I believe. And then multiplied by the weight of your mesh, because your steel is being purchased per ton, right? So best way of doing these kinds of equations, these kinds of calculations, keep the units inside the equation. Once you have the units in the equation, and then final result you have that unit, see if that makes sense. Because if you somehow, oh, I forgot to include the weight of the mesh, means your result will be in terms of meters squared, right? And then that won't make much sense. No, actually, it won't have any units because your floor area divided by the mesh area, it won't have any units. So you need this weight of the mesh to be calculated. So you just do the calculation, you'll probably get a value in terms of kilogram, and then you convert it into tons. So once you have all these numbers, you have the required concrete in terms of cubic meters, you have the total mesh weight in terms of tons, and you know how much it costs per ton and per cubic meter for concrete and steel. You just need to add them all together, and don't forget you have this concrete fixing price of $1,000, okay? So you have this value over here. In terms of value, I think in this recap session, I just want to try to go through again the method instead of the numbers. So just make sure everyone's on the same page with the method. So next option, for the next question, question 1B asks now about the walls. Now we've done the floor, now we're looking at the walls. We're given 3 options, right, for the walls. One of it is a double wide brick wall with cavity. So what it is 2 layers of brick, and you have this air cavity in between. Option 2, I believe, is a concrete wall, and option 3 is something called a Dinser wall. I'll go through them after this, so I'll just go through each option one at a time. So considering the brick size is 100 mils by 60 mils by 200 mils, mortar joints of 10 mils and the cavity width of 50 mils, calculate the number of required bricks and the volume of required mortar, 5% extra brick and 25% extra mortar as waste. So you have this price, so the brick is $1.10 each. The cost to construct each brick is $1.25, and then it's $300 per cubic meter of mortar. So again, please pay attention. Sometimes he puts it like this, sometimes he puts it in meter cube. You know, just pay attention to the story. So let's go through the calculation bit over here, right? So first we need to calculate the area of the openings. So remember how we have 2 windows and 1 door. So we can't, for that wall per se, we can't break out the wall. It's not like we built the wall, we break the part where we want to include the windows and then put the windows, right? No, it doesn't work that way. How we do it is we just build around it, provide a space for the window, and then we install the window that way. That's why we can remove that area from the windows and the doors from the calculation in the first place. In terms of the thickness of the wall, so it's 100 mils plus 50 mils plus 150 mils. So what this is because remember the width of the brick is 100 mils, and we have a 50 mil cavity in between. So it's just 100 plus 50 plus 100 because it's a double white brick wall. So if it's a single white brick wall, we don't have that cavity in between. So it's just the width of one particular brick. Okay. So if you add it up, you'll get 250 mils or 0.25 meters. Just convert them into SI units. It's much more easy. Then we can calculate the length of the wall. So the length of a wall is 4 plus 6 plus 4 plus 6. Right, so it's 4 meters by 6 meters. However, we still have to reduce it by 4 times 0.25. Some of you might be wondering, why do we reduce it? What's the use of it, right? So what this is we are trying to accommodate the thickness of the wall. So if you can imagine, I'll do my best impression with a mouse. So if we only do it this way, right? Let's imagine we're living in a one-dimensional world where the walls are one-dimensional. It's just a line. This is what you learn basically in primary school with perimeters and stuff, right? So if we know this is 4 meters and this is 6 meters, for example, perimeter would be 4 plus 6 plus 4 plus 6 with 20. But in this case, our line is in 3 dimensions. So this thing has thickness over here. So this thing has thickness, the walls. So what this 0.25 meter is trying to get rid of is these parts over here, because now you have overlaps. Right? So if we don't reduce it, then we basically count these corner pieces twice, for example, right? So in that case, we have to subtract it by 4 times that 0.25, because we know the thickness of one wall is 0.25 meters. So 0.25, right? And then also same goes over here. Okay, so now we know the length of the wall, and we know the height of the storage unit, and we know how much opening there is. So we can simply calculate 19 times 2.8, which is the height, minus 5.94, which is the area of the openings, and that should give you your net area of the wall. Now we have to calculate the surface area of one brick, including the mortar. So what we are trying to do is we are trying to calculate, say we have this brick over here, right? It is 0.2 long and 0.06 tall. So we want to find the surface area of one mortar and of one brick. So that includes the mortar over here. I'll just put ink. So we do it that way. Right? So we know that one brick will be 0.0147 square meters. And the number of required bricks, including the waste, we can just calculate it. So the area of the wall is 47.26. And we know that the surface area of one brick is only 0.0147. So essentially, just by calculating the area divided by the number of bricks, the area of the bricks, multiplied by the layers, and multiplied by your waste percentage, taking that into account, you can get the number of bricks over here, which is 6752. Okay, next, we want to get, once we calculate the number of bricks, we need to calculate how much mortar we need, right? So in this case, the required mortar for each brick is, so for one brick, let's change back to a brick color. So for one brick over here, so we have a layer over here, right? And then we have this layer on top over here. So everything on the side needs to be covered by mortar. So what mortar is, it's just the glue of your brick. So it's what sticks the brick together. So if you go look at the brick building, that white bit over there, that's what we call a mortar. So the total, the required mortar for each brick. So if you look at it this way, it might seem a bit confusing. What are we trying to do over here? Because we don't have any units, we don't know what these formulas are, right? So what this is trying to say is, let's try break this equation down, okay? So 0.1 times 0.01 multiplied by 0.2. What it's trying to say is which side of the brick are we trying to put mortar on? So if this is a cube, so imagine the brick as a prism of sorts. So if this is 100, this is 200, and we know this is 60? Yep, I think it's 60. So if we know this dimension over here, 0.1 by 0.2, this part of the mortar that we put it on is the bottom and the top bit, right? So it's just this part over here. So you put mortar on top, which means you get the number of bricks for that side. Next, if we do it over here, where it's 0.1 multiplied by 0.06 multiplied by 0.01, what it's trying to say is we're putting mortar on this side, right? So we don't put mortar on the face of the brick. There's no point. We're not gluing it to anything, right? So we're just putting it on the sides, okay? And then you might wonder, what's this last bit over here? Why do we have this 0.01 again? So what this is doing is, if we put mortar, so if we put mortar on a face of a brick like that, right? And then we put it on over here, and then over here. So this 0.01 is trying to accommodate this section over here. Otherwise we have gaps, all that small gaps, all over the building, right? Which doesn't make sense. So that 0.01 will go through this part over there, this green bit here, okay? So then from there, we know that each brick will require this certain amount of mortar. And then we know how many bricks we need to paste together. And then we know how much waste there is, which is 25%. So we can just simply calculate it that way, chuck it in your calculator stuff. Next, cost of the wall using bricks. So once we want to calculate how much it will cost, so over here, we can see, okay, this 6752 part over here, when we want to calculate the number of bricks. This $1.10 is the cost for one particular brick, and this $1.25 is the cost to install that brick. So please remember to include those things together, okay? And this bit over here is the cost for the mortar. and it will result in this $16,550.90. Okay, is it clear so far? Make sense? Okay, good. Moving on. Next, we have option 2. So now we use concrete blocks and fill it with fresh concrete. So if the blocks are 400 mils by 200 mils by 200 mils, right? And the mortar joint is 10 mils. So calculate the number of required blocks, allowing 10% for waste, and then the amount of fresh concrete required to block the holes. The holes of a concrete block include around 70% of its whole volume. So what it's saying is the concrete has holes in it, and then that hole is 70% of the block, essentially, right? So if it's $6 per block, including delivery, $550 for the construction of each block, $600 for each cubic meter of concrete, and $300 for each cubic meter of mortar. And it's already said that 1.5 cubic meters of mortar is required. So praise the Lord, you don't have to calculate it like just then. So what will be the block laying cost of this storage, allowing 5% extra concrete for waste? So we have a 10% allocation for waste in terms of the blocks, and then 5% concrete for waste, fresh concrete. Okay, so now our new area of the wall, we have to calculate it again. So it's going to be 47.82 square meter. If we look back over here, it might be a bit different, right? So, it's a bit different. It's 47.26 over here, and it's 47.82 over here. So that's because of that difference in thickness, because we only use one layer of concrete. The surface area of one block, including mortar, it'll be 0.4 plus 0.01 multiplied by 0.2 plus 0.01. Again, just how much area of one concrete plus the mortars of 10 mils. And the number of required bricks, including waste, it will be, so you use the same calculation as the bricks, okay? The whole volume of wall, so again, you just calculate 47.82 multiplied by 0.2. It'll give you that wall volume. And so this wall volume, the point of this bit over here is to calculate the amount of fresh concrete required, which is 0.7. So the blocks are 70% empty. So you just do it that way. And then you need 5% extra for waste. So now you have the volume of concrete over here. You can just calculate how much concrete is needed, and then you add the cost for each block of concrete. And also you include the cost of mortar. So over here you see this is the concrete block price. This is your mortar, and this would be the fresh concrete to fill the concrete walls. So essentially with this section, with this question over here, you will learn a bit about the different construction methods for walls, and then from there you can calculate how much of something do we need, okay? Next, we move on to this 200 mil Dinsel wall fill. So Dinsel walls are this new technology. So with Dinsel walls, it's a type of formwork, but that formwork we leave it on site. So it's sort of like a plastic formwork that we have. And then you fill the inside with concrete, and then you have this rail underneath where you can slide the formwork in and out. So the question asks how many square meters of Dinsel panel and how many linear meters of guide track are required. So assuming $95 per square meter and $25 for the guide track, $600 for concrete and $35 for labor, and 5% extra concrete for waste, right? So you can see how the if we simplify the construction method that we select, we get into a calculation that is much simpler and less prone to error. So imagine if we're building the same wall and then we don't have much knowledge, say about construction equipment, and we are faced with this problem, right? And then we are given an option, okay, go for a brick wall or this Dinsel wall. We might just go for the Dinsel wall because it's just much easier to calculate and much easier to control, right? Instead of the bricks. We don't know, if we buy 6,752 bricks, if one gets lost, we don't know where it goes, right? So again, the area of the wall remains the same as option 2 because it's the same thickness, which is 200 mils. length of the wall and the whole volume of the wall is also the same. So we can calculate the required volume of concrete. So the reason why we don't multiply it by 0.7 is because denser walls is generally doesn't have that thickness. So the thickness actually comes from the concrete we pour inside that denser wall itself, and the connections between the two faces of that denser panel is a sort of negligible. Okay, it won't make much of a difference. So if you want to use a denser wall, we know that it's $95 per square meter for the denser panel itself, right? And then the guide track would be in terms of $25 per linear meter. So if we go back to the question, the guide track is $25 per linear meter. So we don't have to, so we don't need to convert this 19.2 into an area. So we just take the length plus the amount of concrete needed and also your installation costs. So it will result in this particular number over here. Okay. Any questions so far? No? All good? Moving on. Okay. Now we have the floor, we have the walls. Now we want to do the roof. So the roof is $100 for per square meter for the fixing and all the stuff. It's $600 and $3,800 per ton and per meter cube for the concrete and the steel. So what is the construction cost of the roof, allowing 5% extra concrete and 20% extra steel? So, oh shit, forgot to include that one. Anyway, essentially, we move back to the question. I'll just do it this way. Let's keep it. Let's open the questions. So, if we go back up here. So, let's just copy paste this. Copy paste. Move it over there. And then paste. Good, magic. And then display settings. So, through the width of the roof, we need 40 steel bars because we know the spacing of each section. And we need 60 steel bars with the length of 4 meters, right? So, because the dimension of your building is 4 by 6. Yep, 4 by 6. And we know that we need it every 100 mils. So in terms of 6 meters, we will need, at 100 mils spacing, we will need 60 of them. And it has to span the length of the building. So it must go like that, right? And then the ones over here, it has to go that way. Okay? So, moving on. So in total, we will need 480 meters of steel, N16 required. And we know that for an well, it should be given, but an N16 steel bar, it weighs 1.618 kilograms per meter. And we need that extra 20% as waste. Then we calculate the total mesh weight again, but this time for an SL81 with the SL81 data, obviously. And that would be 209.32 kilograms. So you use the same method as previously, okay? In terms of the volume of concrete, you just need to calculate essentially length times width times the depth, multiplied by that additional 5%, and that will give you 5.04 cubic meters. Then you can just calculate all the associated costs. So if you want to calculate total cost again, we'll just need to calculate ground slab, cost of the wall and the roof. But remember, in terms of the wall, we have different types of walls. So we have different options and we just need to calculate that over there. Okay. So if the question asks, say, so you can see how this question can be sort of modified in a lot of different ways. It could be Mosen going, okay, if the client has a budget of $25,000, which one would be the most optimal solution? Or perhaps you can see how that will go, right? Okay, so any questions so far about this? I think it's pretty straightforward once you get it.
I just have a question
Yep.
about part A as well.
Yep.
So, with the mesh included, is all of that information going to be included in the question?
Yeah, usually, yeah.
Okay.
Okay. Well, if you're scared, you have the data from the tutorial, from the lecture notes. Just include those in your summary.
Yeah, because the lecture notes don't mention anything about the mesh and the weight of it or like anything else.
Yeah, so just gather it from over here so you know how much an SL81 thing weigh. SL82, you got it from here. N16, maybe you Google what N14, N12, N18, just have a range, just bring it over there. In terms of the data sheet, so there was some concern during class that because of the number of tables we need to bring, so the number of tables we have, especially for weeks 8, 9, and 10, right? There was a concern about we can't fit it on, say, 2 pieces of A4 two-sided, right? But Mosen included a PDF with all the tables, but the tables are not labeled in terms of which one's table 18, table 19, what does it do, and all that. But he has included it in the announcements page of Moodle. So if you go through it, there's something called Tables PDF. You just download it. What I do in the past with formula sheets with no description of anything, especially when I did it, for example, for, what was it? Fluids, I think. So in fluid dynamics, they provided you with a formula sheet, but they didn't give you a description of what the formula is. So just print it out, take a pen, just write on top of the formula what that formula is, so that you know, essentially, because you still can bring that note into class. Okay, so next, construction sustainability. I don't have much to talk about over here. Just this key part over here. This is all you have to know. But the hard bit about this section over here is you have to know where to apply it to. Okay? In the past, I've not seen the finals, what it looks like, but I can assure you, in the past, the question always looks like you're given an image with a, like a project or something, say, talk about UNSW or whatever that is, and then they just ask you, how can we improve the sustainability of this project? So, best way of doing it, you go through this one at a time, like a checklist. So you go, what can I replace? What can I reduce? What can I reuse? What I can re-engineer? What can I reclaim? And how can I re-educate? Right? So, in terms of hierarchy, going top to bottom, it gets a bit harder and harder, because if you go through the re-engineer, reclaim, you need to put in that much level amount of work. And also, in terms of replace, reduce, reuse, and re-engineer, you can't really do it when the project's already going. It's a bit harder to do it. So you can imagine if the building's halfway up and then you have to re-engineer something, it might be too much of a hassle to do. So just bear that in mind. There are different levels where once this building reaches a certain stage, some type of sustainability types, you can't use them anymore. Okay? Hopefully that's clear. So one tip I have about this topic over here, if it comes up, just have a read of some sustainability projects somewhere, get some inspiration, different technologies, different all those kind of things, especially from your assignment. If you did your assignment properly with the sustainability part, you've done some research about how can I improve the sustainability of a certain project. So just have that in mind, and maybe you can include those in your assignment or your finals, sorry. Okay, any questions? Nope. Okay, so Next, we move on to construction equipment and economics. I'll just go through these very quickly. So I'll do one question each for the different equipment. So I think there's 6 or 7 of them. I'll just go through them very quickly because it's probably still fresh in your mind. So first question talks about excavators. Okay, so we have the different bucket sizes and we want to excavate this 40,000 cubic meters with an average depth of 4 meters. And the maximum digging depth is different for the small and medium excavators. So you have this 4 meters for small excavator and the medium excavator is for 5.7 meters. They work 45 minutes per hour. So swing angle is 180 degrees and your bucket fill factor is 0.9. And it's just asking if it's actually worth it to upgrade to a medium excavator if it's 30% more expensive than a small size excavator. So that's essentially the question. Please expect these kinds of questions to come up. These are the most common questions in terms of format. So if we go look at our tutorial questions in the past, sometimes it's very simple. They just give you wheel loader, they give you all the information in bullet points, but sometimes you have to extract that information from a particular paragraph or something. Okay. So table 1, table 3, over here you have the standard cycles, so the number of cycles for different excavators. So you just need to match the bucket sizes over here. And then you match the type of material. If it's not given, please pay attention. If it's not given, please use the average value, okay? The swing depth factor over here, you have the depth of cut over here, which is the ratio between the average depth divided by your maximum depth. Your swing angle is probably given. And if this depth of cut is not, so if it, say, it lies in between, say 60%, then you have to do some linear interpolation, okay? So let's say if it's 45 degrees, if it's 60, so it's between 50 and 70, so you know it's probably halfway between 1.28 and 1.16. So that is 1.22? Yeah, 1.22, okay? So yeah, please pay attention to that. So essentially, with this formula, excavators, it's P equals the cycles multiplied by your bucket size, multiplied by your swing depth factor, multiplied by the volume of your bucket itself, and multiplied by your efficiency. There is some sort of a pattern between different equipments. I'll go through it after this, but essentially you just have to get all the data from the tables, and then just multiply them together to get the production rate. So once you do it for the small excavator and then you do it for the medium excavator, you get these two values where you can compare. Okay, so P for the small one is 97.54 and P for medium is 121.82. And then we bear in mind that it costs 30% more for the medium excavator compared to the small excavator. So we just want to see if it's worth it or not. Okay. So the production rate, if it turns out, it's only 25% more than a small excavator, so it doesn't actually make much sense to hire the medium excavator. Okay. So that gives you so that once you take that small excavator, you know how much is the production rate. You can sort of find out how many hours it needs and the number of days. Okay. Next, we go through in terms of loaders. So in terms of loaders, here we can see we don't have a swing depth factor because the loader doesn't turn. So best way I remember it, I still remember it till this day. I did the course in 2019 or something. But easiest way to remember an excavator, a loader, and a dozer is you just get rid of one variable from the equation. So if your excavator is P equals CB SVE, in a loader, it doesn't swing, so you get rid of the S, and then in a loader, you don't have a bucket, so you get rid of the B, right? So you just have the volume of how much you push for a dozer, okay? So in terms of loader, you just need to calculate it this way. You take it from a table as well. So yeah, easy. Next, dozer, case in point, we don't have the bucket fill factor over here. So it's just cycle, the volume, and then the efficiency, okay? However, in Dozer, the complication comes when you have to calculate the fixed time, the push time, and the return time. So all of this will come from a table, which is over here. The fixed time, it comes from this section over here. It will say, okay, it's a direct drive transmission. Is it a hard digging thing? You just take the amount of time. And then in terms of operating speed, you just take it as whatever this thing is. So if it's 20 meters hard material, then you take the first bit for the push. And then for this return bit, you just take 30 meters or less, okay? It's pretty simple, I think. Okay, am I going too fast? All good? Okay, moving on. So we can calculate our push time and our return time because it is the same. We use the same speed. It's totally up to you whether you want to convert it from kilometers to meters or meters to kilometers. Doesn't matter. Essentially, just try to keep the units the same. Next, we can just do it, all of it. And then in terms of the blade load, we need to take this formula with us into the finals, which is 0.375 multiplied by that particular dimension. And your height would be the average height. So you can imagine the mound would be a bit different. I'll just draw it. So the mound, it could look, say, something like that. Say the mound looks something like that. So you have H1 over here, H1, H2, and then you have, say, W1, and say W2. So what that is trying to make it into a good rectangle with all the average values in it. So you do the calculation and it should give you this particular value. Easy. So with this equipment calculation part, just bring the formula in and then just try to fill that formula. So fill all the numbers in it, okay? So if production rate is more than that, if it's 50 meters, then what changed is will only be the push and the return speed. So with those, is the main thing I think is either number one, the question asks you to change the distance where it's gonna push, or number two, the main difference will be from changing the blade, and then that blade will inherently change the capacity in which it can push. Okay. Next, we have a wheel loader. So another thing like this would probably come up. So in terms of questions like this, it's where we have two equipments working at the same time. So we have a rear dump truck and then also a wheel loader. And then once you calculate that, you can find out, okay, so to fill the one truck, how many bucket loads it needs. So you just see how long it takes to put in the amount of soil. And then you can calculate the loading time from there. So the loading time of a truck, it can come from either how much time it needs for a loader to, say, put the amount of soil inside the truck. In this case, it takes 15 minutes, right? Or number two, it's just given to you. Loading time is 5 minutes, 10 minutes, whatever, okay? But most of the time, try to expect something like this to come up, okay? Next, we have the hauling time of the truck, which is just distance divided by speed. It's pretty simple. And then you calculate the truck cycle time. So cycle is for a truck to load, go to the dump site, come back, and then load it, go to the dump site, dump it, and then come back, okay? So in this case, if each truckload is 20 cubic meters, so 100 cubic meters would be 5 truckloads, so you can find out how long it will take to do that entire cycle. So the main thing with this is we know we only have one truck. That's the main assumption that we have, and we only have one wheel loader. So if we have multiple wheel loaders, it'll probably just decrease the amount of loading time because it'll be faster to load the truck if it can load it simultaneously. And if it has 2 or more trucks, then you have to consider, so in one cycle, how long it will take, okay? Next, we go into to an engine scraper. So with engine scraper, we use tables 10, 11, and 12. So with 10, 11, and 12, we just find, so scrapers work essentially like dozers. Dozers have the pushers, say the blade in front. Scrapers have them in the middle. But essentially it works about the same way. That's why the variables are the same. So it doesn't swing and it doesn't have a bucket. So that's why we still use the C times V times E, right? The fixed time for a scraper, the positioning, loading, and dumping time all comes from a table. So it comes from this table over here. So you just need to match it, essentially. And the variable time would be the hauling time plus the returning time. So it's just another speed and distance calculation. It's very simple. And then that becomes your variable time. So once you can calculate the production rate, you can find how long it takes to do, say, a certain amount of soil. With rollers, the main thing we need is this formula over here. So we need to know how many cycles, how many passes it will take, the average speed, the compacting width, and also the thickness, and your job efficiency. So N would be the number of passes, W would be the width, S would be the speed, T is the thickness of the soil, and E would be your efficiency. So if, say, the question asks you if we are doing, say, a certain field, how long it will take, then you just need to adjust it accordingly. Next, with motor graders, essentially, it's about the same thing as a roller. You just have to change bits and pieces of it. So with this course, it's not typically a hard course, but it's a bit hard because you have to get that final answer right. So just try to get that calculation as accurate as possible. Use 3 or 4 decimal places if you like, but the more the better, to be honest. So next we move on to this depreciation calculation. Just want to review a bit about some depreciation. So straight line method, very simple. Calculate the number of, calculate the total depreciation. And your total depreciation is your initial cost minus your tire life, tire cost minus your salvage value. And then you just divide it by the total number of years. So if it's 5 years, 6 years, 7 years, whatever, you just need to do it that way. So it's uniform. In terms of the sum of the years digits method, remember to keep the number on top in reverse order. So if it's year 1, you take the biggest year. So let's say your equipment life is 7 years, like in this case. In year 1, you will take it as 7. Year 2, you will take it as 6, 3 as 5, so on and so forth. Okay? Please don't confuse it with something else. So the main thing with this, best way of looking at it, you want to take the most amount of depreciation at the beginning of the ownership, right? So it doesn't make sense if your top number over here is 1. So you do it, and then you get up to the 7, and then you have all that basically. Next, with the double declining balance method, this is where it's a bit different. You don't calculate the total depreciation, but moreover, you calculate the book value at the beginning of the year. So this book value, this BV, you have to calculate, okay, so how much is this equipment worth? And then minus that depreciation, that will give you the depreciation of the book value of the next year, right? And then you base off the depreciation calculation from each following year. The main key point with this method, if it's asked from you, is pay attention to the book value all the time. Make sure the book value doesn't go below the salvage value. So that book value can go down below that salvage value anyway. It could happen, it doesn't have to happen at the last year, it could happen in the 3rd year, the 4th year, anyway. It just depends on how much depreciation is happening. If the depreciation, if the book value goes below our salvage value, then we have to just match it to basically whenever it goes below the salvage value, we match that last bit to the salvage value, and then everything after that becomes 0. Okay, I'll have another question in question after this with all that. Okay. So this is a good example. Say over here, we see how the salvage value is supposed to be 18,000, but in year 6 we go 17,530.96. So essentially, we just need to get rid of this depreciation and move a step back and change it, change the book value to match that $18,000, and that should give you $6,543.35. In terms of the next year, so if you remember this question, it has 7 years. So this equipment has 7 years of life. So that last bit, we don't get any depreciation off of it because it already reaches that salvage value. So salvage value, mainly it's how much it's worth after a long period of time. So that salvage values could be a lot of things. It could mean just the weight of the steel of the equipment it has. It could be how much it costs, say how much it will be worth if we part out the excavator, for example, or what. So next we have this modified acceleration cost recovery system method. So here again we use another table. I hope you don't get sick of tables after this course, because you'll see probably a bit more in the future. But this one is much easier. You just need to calculate the total depreciation and then go C1, C2. You just need to go based off the numbers you have on here. Okay, so question 4. This would be something, again, another calculation question that will probably come up. So we need to calculate this production rate, how much it will cost if we want to list out a particular equipment to, say, someone to do a certain project. You'll probably get a list like this somewhere in the question. And the main thing I need you to remember all the time is we need to calculate 2 things. We need to calculate number 1, our ownership cost, and number 2, our operation cost. In terms of the formula itself, because I think you will have enough space on your cheat sheet, don't write the abbreviation of it, just write the full word of it. Say, for example, in terms of this, you go, okay, so this is the average value equals the initial cost, and then this is multiplied by the number of years plus 1, and then this is your salvage value, and n would be, again, the number of years. Or at least you have a legend on the side that says what each variable is, or even like an arrow just showing, okay, what's IC, what's S, what's N, right? So it just prevents confusion. So in this particular question, what you need is number 1, your equation, and number 2 is your, you being careful not to pick the wrong number and chuck it into the calculation, because the number that comes out, it won't look strange to you because all the numbers will be in decimals, and you won't, because if we do physics, right, and then we do this calculation, we put in the wrong number, you'll probably come up to a number that doesn't make much sense, right? So for example, if you have a mouse that starts running and then you put in the wrong number and then this mouse starts to have the momentum of an elephant or something, then it doesn't make sense, right? But in this case, if you put in the wrong number just a little bit, say it'll just probably show like $9,000 or $13,000. So yeah, we can't really tell. So just pay attention to all that, okay? So first, calculate our investment cost for our ownership, our insurance, tax and storage costs, and our depreciation, right? And then with this depreciation, we just need to match it to whatever method has been selected or have been decided in the question. In this case, it's going to be using the sum of the years digits method. So we can get this ownership cost per hour, okay? This ownership cost over here, it generally, this calculation, if you look at this depreciation, insurance, and also investment cost, it's going to be per year. It's always best to convert it to per hour because your production rate in the future, it would be in terms of hour. Next, it's our operation costs. We have 6 things. Again, go through them like a checklist. Just go tick, 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 tick through them. Okay. So fuel costs, we need the horsepower, the time factor, the fuel price, and then also the this POC times FCR. So what this is, it comes from a table. So POC is the percentage of operation condition. So how many percent is in favorable condition, how many percent is an average, how many percent is unfavorable, and we have all these equipment types. So we just need to match it, say, so for example, if over here, oh, it doesn't, it says 100% favorable, I'll just make up an example. For example, if we have 50% favorable and 50% average, and we have, say, an excavator, our fuel consumption rate, it will just be 50% multiplied by 0.13 and 50% multiplied by 0.15. And that gives you like a sort of a weighted average of the weighted average of the fuel consumption rate. Okay, is that clear so far? Okay, so going from fuel consumption rate to service cost, the main difference, you use the same equation, but you have this service cost factor, and it comes from table 20. It's very simple. So it's the same for all equipment. For favorable, it's 20%, 30%, 50%, so on and so forth. And then once you calculate it, you can get the service cost, dollars per hour. Repair costs, you use this lifetime repair cost factor. And you might see over here, the repair cost, it uses this, something that looks like a sum of the years digits method. But the main difference over here is that the year digit is not in inverse order, okay? So what it's trying to say is things don't get broken when it's new, right? So things get broken more and more as it gets older. So if it's, say if it's on the first year and then you put in 6 divided by whatever that number is, it's saying that why is it breaking more in the first year? It doesn't make much sense, right? So if it's on, say, the first year of its life, then it's probably have to be 1 divided by this 1 plus 2 plus 3 and all that. So it has the least amount of weight. Next, we have the tire cost, which is just this formula over here, 1.15 multiplied by the price of a set of tires divided by the expected tire life, and you get that tire cost over there. Operator cost is $27 an hour, it's probably given. And with special items costs, we might have multiple special items, so we have to calculate them separately and then just add them all up at the end. So in this case, you only have one, which is the bucket tooth, and we know the expected life of the bucket tooth. Okay. So once you have all that, you can just calculate everything, just add them all up, and then we have the 60% overhead costs. You just need to multiply it. It gives you $144.10. And from there, we can calculate how much it costs per LCM. And then from there, you know the project's 10,000 LCM, calculate it. We know the production rate of the loader. And then we can find out how many days it will take. Okay? It's pretty simple. So, from here, just want to give you one additional stuff that you cannot forget from weeks 1 to week 4 is this calculation over here. I don't know if he's going to give you the bank cubic meter, if he's going to have some assumed knowledge. So the main thing with this equations over here is the you're assumed to know weeks 1 to week 4, and because the construction work includes some excavation, for example, and it might use some bank volume, so you have to convert them appropriately. So this swell, well, it never hurts to just bring it on your formula sheet, whether you use it or not. So yeah. Okay, and then finally your soil shrinkage. So if you want to finally put it in, we don't know if Mosen's going to go, because essentially the process the same, it's just reverse. If you're doing excavation, it's just loader to truck and then truck goes away. But if it's going to fill, then it's just truck and then loader to the ground, which is about the same thing, right? Okay, that's all the content. I hopefully that's like a good refresh of your mind for your finals. Finals will be on when was it? When it's gonna be? Can't remember. 10th?
Next Saturday.
Next Saturday is 17th. Yep, so on the 17th. of. Okay, so questions. I'll just show you the thing. I'll show you the PDF file. So this is what the PDF file look like. It has sort of a description of it, but it's because someone said that how can they fit 20 tables on a page? And then I think Merson took the challenge and then he proved that he can. So essentially he gave it to you. You can just print this out and then label it however you want. So yeah, you have this wind velocity and the design wind pressure. This is for, so these two things, these are for the permanent structures, okay? Over here it's all for the equipment prices and all that. Yeah, it's not the best arrangement, I would say. It's not as neat as I would like it, but it's all there, okay? Questions? No questions? Okay. I'll just stop the recording.